Welcome all. So, last time we started with the approximations for predicting the blast pressure. So, we looked into the different formulations given by the different researchers over the period of time. The approximations are empirical in nature, and what they are trying to do is that they are trying to fit the equations. Okay. They are trying to fit the equations in the blast profile that they are able to get. Okay. So, the data that were used were from either literature or from the data that the researchers were able to perform the experiments. Okay. So, using this data, different researchers tried to fit the different empirical equations. Okay. So, these are the good approximations for the blast pressure. Okay. But the only thing is that all equations have certain limit depending upon the pressure profile, depending upon the different atmospheric conditions, depending upon the different factors. Okay. So, each equations come with its own set of limitations. So, whenever we are trying to use these equations, we have to see the limitations and use an approximate equation or use an appropriate equations where those limitations are being followed. One more thing is the units. Okay. So, the approximations are made and an empirical equation is being used. Okay. So, the curve fitting is done in a particular unit only. Okay. So, whenever we are trying to use these equations, the original form of the equation should be used in the particular values. Okay. Otherwise, it will be a mismatch depending upon the constants that the equations have. Okay. One more point of interest in this equations was that all the equations somehow try to relate the proximity factor with respect to the pressure. Okay. So, in all the equations, the proximity factors plays an vital role. Only thing is that the different equations are becoming more and more complex as the number of data are being the number of available data becomes more and more predominant. Okay. So, we will continue from there. Okay. So, last time we looked into the pressure equations, now we will look into the duration of the blast loading. Okay. So, last time we looked into the pressure, now we will look into the time part. Okay. So, if we want to analyze the blast loading, we need both the pressure and the time. Okay. So, previous equations were dealing with the pressure parts, now we are dealing with the time part also. So, for analyzing blast loading, explosions are often idealized to include only the positive overpressure phase, okay, which simplifies the assessment of the structural response. Okay. What does it mean is that normally when a blast occurs, it will have a Friedlander profile. Okay. Okay. So, there will be T positive, T negative. Okay. In our analysis, what we do is that we simplify it using a triangular pulse. Okay. So, using a triangular loading, so what we do is that we take the positive phase duration, we integrate it. Okay. So, P is integrated over time t. Okay. And same impulse is maintained out here. Okay. So, the area under the curve remains the same, and we also maintain the magnitude of the pressure. Okay. So, we maintain the magnitude of the pressure, okay, and thereby we get the Td positive. Okay. So, this way we calculate the pressure time signature. Okay. So, for analyzing blast load, explosions are often idealized to include only the positive overpressure. Okay. So, this is what it is mean by this term, and this simplifies the assessment of the structural response. Okay. So, here Td is defined as the time from peak pressure decay to zero overpressure during the positive phase of an explosion. Okay. So, this is how we are trying to analyze the, or we are trying to calculate the Td. Okay. So, there are different equations as we have seen earlier, similar to the pressure equations. There are contemporary equations for calculating the Td also. Okay. So, Henrik proposed this particular equation, okay, in 79. Okay. So, again we can see this equation also has a proximity factor. Okay. So, this equation is again a function with respect to the proximity factors and other constants multiplied to it. Okay. Kinney, okay, we saw earlier that Kinney has a pressure equation also, and similarly he has a Td equation also, a time equation also. Okay. So, again this equation is a function of the proximity factors. Okay. So, this is the non-dimensional value of the proximity factor, okay, and multiplied by a value, it will change back into the time Td. Okay. Sadowski also proposed one similar equations, okay, and Isaac-Vidard also proposed the different equations. Okay. So, here what we did was he tried to broke it into 4 parts depending upon the range of the proximity values. Okay. He proposed 4 equations. Okay. So, here the point to take out is that there are different equations, okay, and all these equations have their own limitations. Okay. Either they are grouped depending upon the proximity values, or they are grouped depending upon the type of the explosive use, atmospheric conditions and other factors. Also they are unit dependent. Okay. So, all the factors that are being used, they are made depending upon the units, okay, and all these equations are somehow related with the proximity factor. Okay. So, these are the good approximations that can be used to estimate the time of the loading, but they should be used carefully, taking into account their limitations as well as the particular unit that they are given in. Okay. So, this way we can use the different equations to categorize our blast loading, okay, the pressure also and the time part also. Now, the effect of the blast loading. So, during an explosion, a pressure bulb forms and a spherical pressure expand outwards. Okay. So, this is how the blast is going to expand outwards. Okay. So, when these waves strike the ground, okay, they reflect and reinforce the incident wave. Okay. So, if this is happening, okay, and if there is a reflection, okay, so what it will do is that there will be a reinforcing effect will form, okay, and that will add to the incident wave, okay, and then travel along the surface with greater pulse velocity and duration. Okay. So, there will be an increase in the effect of the blast, okay, if there is a reflection from the ground. Okay. So, during an explosion or impact, okay, structural materials are exposed to extremely high pressure over a very short time. Okay. So, during an impact, this is the nature of the loading, and during a blast, this is the nature of the loading, where here the magnitude of the pressure or the force is very high, okay, and the time duration is very small. Okay. So, the structure is exposed to extremely high pressures, okay, in both the events, and it occurs over a very short period of time. Okay. So, what it does is that there is a high loading rate. Okay. So, while dynamic stiffness is similar to static stiffness, okay, the stresses sustained under dynamic loading are significantly higher than those under static condition. Okay. So, this phenomena we have seen as a strain rate effect. Okay. So, what happens is that as the rate of the loading increases, okay, as the rate of the loading increases, the amount of stresses that the system can survive becomes more. Okay. With the increase in the rate of the loading, okay, the amount of stress that the system can survive becomes more. Okay. So, its resistance capacity becomes more. What might happen is that the strain, the value of the strain or the value of the ductility might become less, okay, but stress wise it will increase. Strain wise, okay, or the ductility wise, it might decrease. Okay. So, this is the enhancement in the strength due to the strain rate effect. Okay. So, as we move from the quasi static to the normal loadings like earthquake, then to the impact region, and again to a high strain like blast region, the stiffness of the system and the strength of the system increases significantly. Okay. So, in blast resistant design of structures, okay, the increased material strength under higher loading rate is accounted for by using the dynamic increase factor. Okay. So, if we look into the stress capacity, okay, in the dynamic sense and stress capacity in the static sense, okay, so there will be an increase in this value, okay, and this is known as the dynamic increase factor. Okay. So, for high strain rate event like a blast strain event, we use the enhancement in this capacities. Okay. So, DIF is nothing but the ratio of the dynamic strength with respect to the static strength. Okay. So, in the bending phenomena, if we looked into the steel and concrete, okay, it is roughly increasing from 17 to 19%. Okay. Diagonal tension, we do not account for any increase, though in reality it might increase, but since this phenomena is very complex, we do not take any increase in the factors. Okay. Shear, again a phenomena less understood, so we only take 10% of the increase. Okay. Bond, again concrete, it is not very much well known, so we do not take any advantage due to the dynamic increase factor, and we keep this ratio as the same. Still a bit things are understood, so we take around 17% increase. Okay. Compression, we take 10 to 12% increase. Okay. So, basically if you look into this phenomena, what is interesting is that in reality there will be a dynamic increase factor in the blast event, okay, due to the high increase in the strain rate, but there is a parity in the phenomena what we know and what we do not know. Okay. So, what we know, we try to take the full advantage. Okay. So, here bending is normally well known, so we take 17 to 90% increase in both steel and concrete. Okay. The phenomena which are not very well understood, like diagonal tension, direct shear, okay, we do not try to take that advantage. Okay. Like the bond slip in the concrete. Okay. This is again a phenomena which is not properly understood. Okay. So, we do not try to take the advantage due to the dynamic increase factor. Okay. So, again this is a limitation between the overestimated design. Okay. So, we should have a safe design. Okay. So, here though in reality there might be an increase in the DIF value, but normally we ignore these values. Okay. So, this will give us a design on a higher side only. Okay. Why higher side? Because these are all the capacity values. Okay. So, capacities values, though in reality they might be more, we are taking in a lesser values. Okay. So, we are assuming a low capacity of the system, okay, though the actual capacity might be higher. So, what we are trying to do is that we are trying to increase our margin of safety out here. Okay. So, dynamic loading. Okay. Static loads are either time dependent or change very slowly over time. Okay. They are applied gradually and remain on the structure for extended period. Okay. For example, live loads and slowly moving loads. Okay. Dynamic loads are highly time dependent, they act over short duration or change rapidly in magnitude or direction. Okay. For example, the machine vibrations, earthquakes, impacts, blast. Okay. So, they are predominantly termed as a dynamic event. Okay. So, under the dynamic loading, okay, the structural response varies with time and is typically evaluated in terms of the displacement velocities and acceleration. Okay. So, this is a typical representation of a dynamic force. Okay. So, again different methods of analysis is being used. Okay. So, blast is a short duration load and it is often referred to as the impulsive load. Okay. So, under the theoretical assumptions, if negative pressure is neglected, okay, and only the positive phase is considered, the blast can be approximated as a triangular load. Okay. So, this is what we are discussing earlier also. So, the literature shows that a structural response to an explosion depends upon its ductility and the natural vibration period. To analyze the dynamic response, we determine the blast wave characteristics, we calculate the structural natural period, we compare the blast wave's positive phase duration with the structural natural period. Okay. So, now here we are trying to look into the formulation of the design charts. Okay. So, now we will take up an case where we will try to design a multi-story building with the structural models. Okay. So, in the multi-story building, a rigid frame construction is preferred for blast resistant structures due to the open internal spaces, okay, strong lateral load resistance, okay, good energy absorption from the plastic hinge formation. Okay. The formation of the dynamic plastic design focuses on industrial buildings like the ammunition storage, bunkers and other type of buildings, single story multi-base structures, okay, like the command centers, okay, data centers, okay, and exposure to moderate blast overpressures. Okay. So, if you are looking into the multi-base structures, we normally take into account the moderate blast overpressure. Okay. So, the key features of the blast resistant frames are they have an exposure to high vertical and horizontal pressure time loads. Okay. So, the pressure time loads, okay, are significantly higher. Okay. There will be inelastic deformation, okay, allowed in the design. Okay. So, mu might be around 5, okay, and theta might be around 2 to 3 degrees. Okay. So, here the plastic design is allowed. Okay. And the blast resistant frame must support operational continuity with minimum post blast repairs. Okay. They should be operational after any significant event, and the post blast repairs. Okay. So, the repair occurring in the system after a blast event should be minimal. Okay. So, these are the design guidelines, okay, that are translated into this design parameters. Okay. So, if the operational continuity is not required, then we can again go for an high ductility value, and we can also increase the value of the permitted rotation. Okay. And if minimal is required, then we have to tighten the value of the ductility and the rotation. Okay. So, from here to here it becomes less operational, okay, less and less operational. So, if you want more operational, we have to tighten the value of the ductility, and we will have to tighten the value of the allowed rotation in the particular system. Okay. So, we have looked into the different methods of the design. Okay. So, now we are dealing with the specific case of a multi-story building. So, we can design the multi-story building using an equivalent single degree of freedom system also. So, what it does? Okay. So, in the single degree of freedom, the equivalent single degree of freedom method, okay, it simplifies a complex structure into a single degree of freedom system for the blast analysis. So, if we look into a multiple story building, okay, if we look into a multi-story building, okay, with multiple bays and multiple stories. Okay. So, this is a complex system, okay, and it has a, this is a multi degree of freedom system. Okay. Okay. So, what we can do is that instead of doing this entire multiple degree of freedom system analysis, which is complex, which is time consuming, we can also employ a single degree of freedom system analysis method and analyze our multi-story building. Okay. So, it simplifies the complex structure into a single degree of freedom system for the blast analysis. So, what are the key parameters required? Okay. So, it requires an equivalent stiffness and mass. Okay. We will have to model this entire multiple degree of freedom system into a equivalent stiffness and mass. Okay. So, what we need to ensure is that we need to ensure that the energy equivalence is with the real structure. Okay. So, the total amount of energy absorbed by this complex structure should be equivalent to whatever single degree of freedom system approximation we are making. Okay. So, the total energy should be the same. Okay. So, there has to be an energy equivalence with the real structure. What does it mean actually? So, if we take a very simple example, okay. Okay. Let us say that we are taking a simple fixed beam. Okay. We keep on adding load to this system. Okay. So, what is naturally going to occur? Okay. So, there might be a formation of two plastic hinges at the end. Okay. So, depending upon the structural configuration, there might be two plastic hinge forms at the end. Okay. So, this is how the structure will now become. Okay. So, if we are seeing the load deformation curve. Okay. So, here this is the first point where the two plastic hinge has formed at the end. Okay. Now, the system is behaving as a simply supported beam. Okay. Now, again if we keep on loading this structure, there will be a third plastic hinge formed at the middle. Okay. So, here the system, we say that the mechanism has been formed and the system can no longer take loads safely. Okay. So, if we put more loads here, the system is going to deflect indefinitely. Okay. So, this is the force deformation curve, okay, or this is what we call as the resistance curve. Okay. So, here the total energy in the system, so the total energy the system can take is this area 1 plus area 2. Okay. So, area 1 plus area 2. Okay. If I have to represent this system using a single degree of freedom system, okay, what I need to do is that I need to make a system such that this total area is maintained. Okay. So, what I will do is that I will keep an equivalent area. Okay. I will try to make an equivalent area keeping the force term constant. Okay. So, this will be my new triangle. Okay. So, if area of A1 A2 equals to half of F, which was same as the previous, times delta D. Okay. I know area A1, I know area A2, F I know. So, I can calculate my delta D. Okay. So, I can construct this curve. Okay. And from this curve I can calculate the value of the equivalent stiffness K. Okay. So, this is the K equivalent. Okay. Similarly, I can calculate the mass equivalent. Okay. So, this complex system, okay, has been represented using a simple energy equivalent system. Okay. So, here I also need to match the displacement and velocity at key points for the kinematic similarity, and we need to idealize the load to preserve external work equivalence. Okay. So, in this way I can change any multi degree of freedom system to a single degree of freedom system, maintaining the energy equivalency. Okay. And I will have to match the displacement and velocity at the key point for the kinematic similarity, and we can idealize the load to preserve the external work equivalence. Okay. Similarly, if we take any frame, okay. So, similarly if we take any frame, okay. So, what we can do is that we can apply load, okay. We can again draw the force deformation curve, and depending upon the different plastic hinge formation, okay, we can calculate the total external work equivalence, okay, and then change this system into an equivalent system, okay, keeping the velocity and the kinematic similarity. Okay. So, this way any multiple degree of system can be changed into an equivalent single degree of freedom system. So, this is very useful when we are trying to design the multi-story building. Okay. So, the resistance function will include Mn, the negative plastic moment, the positive plastic moment, and the bending stiffness. Okay. So, using this single degree of freedom approximation, the displacement response can be calculated, okay, and from the displacement responses the internal shear force, bending moment, and other stresses can be calculated, okay, using the equivalent force method, okay, that we have already discussed. Okay. So, using this methodology, okay, and complex multi-story building, okay, with a multiple degree of freedom system can be broken down into a single degree of freedom system, analyzed and designed very easily. Okay. Okay. So, here this shows what we have discussed earlier. Okay. So, we have taken a fixed beam. Okay. So, this is the how the beam is going to deflect. Okay. Let us assume that a plastic hinge forms at the end. Okay. So, when the plastic hinge forms at the end, okay, after the formation of the plastic hinge at the end, this becomes like a simply supported beam, okay, and after that keep on increasing the load, there will be a plastic hinge formation at the middle, okay, after which it can no longer support the load. Okay. So, this is the original force deformation curve. Okay. So, from here to here it is behaving as a fixed beam, and from here to here it is behaving as a simply supported beam. Okay. So, now the entire thing, what we can do is that we can represent, okay, we can take the total area anywhere, okay, and we have to equivalent this area A1 A2 with the area new area. Okay. Okay. So, this area, this will be area A1, this will be area A2, and this is our new area equivalent. Okay. So, this area needs to be equated. Okay. So, this part is of same, so it can be cancelled out. Okay. And here we can calculate the equivalent spring stiffness. Okay. So, this is the equivalent stiffness, okay, and the mass can be calculated. Okay. So, this way we can take any complex system and change this thing to a multiple degree of freedom system. Okay. So, what is stiffness? Stiffness is the load causing unit deflection at a specific points, okay, and mass, this is the portion of structural mass that participates in the deformation. Okay. So, both these parameters can be calculated using the shape function. Okay. So, complex system represented to a single degree of freedom system. So, same analogy you can use for the multi-story building system design also. Okay. So, here we are showing the transformation factors for the selected one-way elements. Okay. So, here depending upon the different strain range, okay, elastic, elastoplastic, plastic, okay, different mass and stiffness factors are being used. Okay. So, this chart, okay, can be used for the design purpose. Okay. So, these are for the one-way elements. Okay. So, similarly, what we can do is that we can take the Newmark's analytical deformation equation, okay, and we can apply it to the RCC columns, okay, at the ultimate performance level. Okay. So, here this is the Newmark's equation, okay, and these are the different parameters for the Newmark equation, okay, and Xc is the equivalent static deformation, okay, and this is simply calculated using the resistance divided by the stiffness. Okay. So, this way we can calculate the response of the system. Okay. So, in order to calculate the maximum deformation Xm, normally beta is selected to 1, the load independent capacity, and we can simplify the Newmark's equation, okay, and calculate the response of the system. Okay. So, this is again a very powerful equation, okay, which is simplistic in nature and it can be readily used to calculate the response of any system. Okay. So, we can use this approach to design the system. Okay. So, we can use the member design approach, okay, using the peak loads. Okay. What we can do is that we can make an equivalent single degree of freedom model, okay, to design the structural members for blast resistance through the following approach. Okay. We can determine the peak load, okay, such as axial shear and bending moments. Okay. So, peak load equals to the critical load factor times the applied load or the limiting resistance. Okay. Then what we can do is that we can calculate the member resistance for the each member. Okay. So, strength increase factor and the dynamic increase factor we can use. Okay. So, the dynamic strength for the material in flexures we can thus we have multiplied with the strength increase factor and the dynamic increase factor. Okay. So, this is for the bending. Okay. After that we can calculate the depth of the compressive stress block. Okay. After that we can calculate the effective depth of the section and we can calculate the normal resisting moment. Okay. So, this is an step by step for the design of an RCC member. Okay. So, the resistance of a simply supported and fixed unit width cross section is given by this equation. Okay. So, shear strength, again multiplying with the particular factors we can calculate the dynamic shear strength, we can calculate the nominal shear strength and the shear resistance at any given section can be calculated. Okay. After that we define the equivalent single degree of freedom system. So, the equivalent stiffness of the trial section we can calculate using this equation, the trial section's gross moment of inertia, okay, or the second moment of area is given by this equation. The crack moment of area we can calculate. Okay. After that we calculate the average moment of area or second moment of area. Okay. So, here what we are trying to do is that we took the gross second moment of area. Okay. We calculated the cracked second moment of area. Okay. So, our section will be somewhere between the gross and the cracked value. Okay. So, we took the average moment of area, okay, between this two values. Okay. So, we have the elastic limit deflection which is nothing but by resistance divided by the stiffness. So, the actual mass we calculated, okay, and from here we can calculate the effective mass. So, the equivalent mass using the charts. Okay. So, using the charts that we previously provided. So, using this charts, okay, we can calculate the equivalent mass, okay, and then we calculate the equivalent single degree of freedom system. There is the time period of the equivalent single degree of freedom system. Okay. And after that we apply the loads and solve the equivalent single degree of freedom system. Okay. So, the structural members are designed using load combination of blast and conventional loads. Okay. So, we have to apply the conventional loads plus the factors with the blast loads. Okay. The peak deflection of the equivalent system is based on maximum support rotation and the ductility ratio. Okay. So, this is the ductility ratio and the rotations that we were discussing earlier. Okay. So, the dynamic support reactions are calculated and applied to the supporting elements as the loads. Okay. The natural period of the single degree of freedom system is compared to the blast positive phase duration. Okay. So, depending upon whether it is lying, the system will behave in the impulsive regime, in the dynamic regime, or in the low pressure regime, okay, depending upon whether this ratio lies. Okay. So, in the impulsive regime, the response is simplified by equating blast wave kinetic energy to the internal strain energy of the system. Okay. So, this is an approximate method to calculate the response of the system. Okay. So, after that we check the limits of the responses. Okay. So, the response limits are evaluated against the maximum support rotation and the ductility ratio. Okay. If they lie less than the allowed limit, it is okay, or if they are not, again we have to reiterate and design the system. Okay. So, this is an effective and easy method to design the system. Okay. A complex multi-story of degree system we can design by this system, but it has limitations. What are the limitations? Member by member single degree of freedom system analysis is common and reliable for the blast resistant design. Okay. So, though the system is formed of multiple degrees of freedom system, here what we are doing is that we are breaking the system and we are doing a member by member analysis. Okay. This method may miss some complexities of the full structural dynamic responses. Okay. So, what we have done is that we have taken a full system, a full complex system, and we are breaking it down into member by member and designing it. Okay. So, one thing is that we have to do it for the different member configuration. Again, there might be some interaction between these things which might be missed during this analysis. Okay. The single degree of freedom system assumes supports are perfectly stiff, which is not always true. Okay. And the structural elements can interact, causing coupled dynamic responses. Okay. So, ignoring coupling when natural frequencies are close can lead to unsafe, unconservative results. Okay. So, these are the limitations, okay, when we are trying to design a complex multiple degree system using the single degree of freedom approximation. Okay. The good thing about this approximation is that it is fast, it is reliable, and it can design a very complex system with minimal ease. The limitations is that some of the complex interactions, some of the complex behavior, and when the modes are closely spaced or there is an interaction between the elements at the joint level, they might be ignored. Okay. So, we always have to design these things taking into precautions. Okay. If we have resources, if the time permits, we can do a complex analysis. Okay. Or if the time is not permitting, what we can do is that we can rely on this easy, fast and reliable methods of analysis. So, I will request you to look into these methods and then practice it. We will continue with in the next time. Thank you.